I'm Yan, an MPhil candidate at Australian National University. The title of our research paper is Query by Sketch, Scaling Shortest Path Graph Queries on Very Large Networks. Computing shortest path is a fundamental operation for understanding how vertices are connected in a graph. Previously, to explain the connection between two vertices, the point-to-point shortest path problem, which finds one shortest path or shortest distance between two vertices, has been widely studied. But vertices with the same distance may be connected by different shortest path structure. Consider these three graphs depicted in this figure. In graph A, there's only one shortest path between U and V. In B and C, there are 3 and 7 shortest paths respectively. The shortest distance or one shortest path between U and V is insufficient for us to distinguish vertex U and V in these three different scenarios, since the shortest distances between U and V are all 3. A straightforward way is to enumerate all shortest paths between two vertices, but this will lead to overlapped paths and is combinatorially challenging. For example, in graph C, each vertex appears on multiple shortest paths. Therefore, we studied the shortest path graph problem in our paper. To understand how two vertices are connected, we compute a shortest path graph which contains exactly all the shortest paths between two vertices. It is worth to notice that such a shortest path graph can also be applied to support the computation of other problems. For example, the shortest path rerouting problems find a rerouting sequence from one shortest path to another that only differs in one vertex. Computing such a rerouting sequence enables the robust design of networks and also allows us to find critical edges and vertices. However, computing such a shortest path graph is computationally expensive since all shortest paths between two vertices should be found. The Dijkstra and breadth first search are algorithms that spring to mind when talking about computing shortest paths. These two algorithms are search-based. In other words, there's no pre-computation and all the shortest paths are computed on the fly. They both have a high query time complexity. When we require low latency on large-scale networks, such search-based methods are obviously inefficient in answering queries. In order to speed up the online computation, labeling-based methods have been proposed. These methods pre-computed labels such that certain properties hold and answer the point-to-point shortest path or distance query by examining the labeling information without searching on the graph. The state-of-the-art work is print landmark labeling. Each vertex keeps labels which are its distances to other vertices. Redundant distances are print in this work. We extend this work and propose print path labeling to support the computation of shortest path graph. We also propose parent print path labeling, which keeps additional parent information in labels. Though this often further accelerates query time, it makes the space complexity for storing labels larger. And previous work shows that storing distance is prohibitive for large graphs. Storing labels for computing every shortest path is hardly feasible due to the demand for much more space. For both these methods, their labeling spaces are hundreds of times larger than the origin graph. So we can see there's a trade-off between query time and labeling size, and we are motivated to develop a hybrid method. Concretely speaking, our goal is to develop a hybrid method which scales over networks with millions or billions of vertices and edges. It should be query time efficient. It can answer a query on networks in less than 1 second on average, so as to support different applications. And it should be labeling space efficient. The labeling space should be comparable with the origin graph. In our paper, we propose another method called Query by Sketch. This figure illustrates the overview of Query by Sketch. It consists of 3 key ideas: labeling scheme, fast sketching, and guided searching. Given a graph, we pre-compute and store a labeling scheme using a small number of landmarks. When we are queried, we first compute a sketch which summarizes the structure of shortest path in this query according to labeling, and search on the graph under the guidance of the sketch. We'll introduce these three key ideas one by one. The first key idea of query by sketch is a labeling scheme. We compute such a labeling scheme so as to encode the paths between vertices in this graph. We know that it is space-consuming to encode all pair distance information, such as labeling imprint landmark labeling. And our target is to encode important distance information. Specifically, we select a small set of vertices, such as landmarks, to construct such a labeling scheme. Distances or paths in relating to these landmarks are considered to be important. This labeling consists of two parts. The first part is a metagraph, which compactly represents the shortest paths between landmarks. The metagraph is a weighted graph. Each edge represents the shortest path between landmarks in the origin graph, and the weight of the edge is the length of shortest path. In this example graph, we select vertices in green as landmarks, and here we have a metagraph. The edge 1, 3 is assigned with a weight 2, since the shortest distance between 1 and 3 is 2. Second part is a path labeling, which compactly represents the shortest paths between landmarks and other vertices. Each vertex which is not a landmark have a label with several entries. Each entry shows us the distance between this vertex and a landmark. Here, let us have a look at the label of vertex 4. It contains 1, 1, which means that the distance between vertex 4 and landmark 1 is 1. It also contains 3, 1, which means that the distance between 4 and landmark 3 is 1. Instead of storing all the shortest distance between landmarks or between landmarks and other vertices, we choose to add entries if and only if there's at least one shortest path which does not go through other landmarks. In this example, the shortest paths between 2 and 4 all go through other landmarks. Then in the label of vertex 4, we do not add an entry which indicates the shortest distance between 4 and landmark 2. Such a precise way of labeling does not violate the precision of our labeling, which captures path information, and it helps us avoid redundancy. We compute our labeling scheme by performing a breadth-first search rooted at each landmark. Here A shows the breadth-first search rooted at landmark 1. Vertices in yellow will have an entry from landmark 1 in their labels, and other vertices are not labeled by landmark 1 since all shortest paths between these vertices and landmark 1 go through landmark 2 and 3. Notice that our way of labeling is not to construct labels and remove redundant ones. We construct only useful labels. Also, in this breadth-first search, we can compute all the edges related to landmark 1 in the metagraph. Similarly, we also perform breadth-first search rooted at landmark 2 and 3. Therefore, the labeling scheme has been constructed. The second key idea of query by sketch is fast sketching. We compute a sketch to summarize the important structure of shortest paths in a query answer. It is based on labeling scheme which we just constructed, and it provides an efficient and principled way of searching, which we are going to do next. Here we show the sketch for answering the shortest path graph query between vertex 6 and 11. The distance in this sketch is 5. It is an upper bound of the actual distance between 6 and 11 in the graph based on triangle inequality. If the actual distance is 5, as estimated by this sketch, all landmarks in this sketch are on the shortest path between 6 and 11. The last key idea of query by sketch is the guided searching. We conduct a search under the guidance provided by labeling and sketch. Up to now, our labeling scheme and the sketch have already shown us the structure of shortest paths between vertices through landmarks. We perform the search on the specified graph in which landmarks are removed. We show the specified graph in this example in figure B. Then we try to compute the shortest path on the specified graph under the upper bound provided by the sketch. We find edges in E. This is a part of the shortest path graph. It is also possible that we find no shortest path, and this implies that landmarks are on all the shortest paths between these vertices. If we find no shortest path on the specified graph, or the length of shortest path is the same as estimated distance in the sketch, we know that paths captured by the sketch are also shortest paths, and we need to search these shortest paths which go through landmarks. In Figure E, we find shortest paths which are captured by the sketch, and we merge these two parts to get the shortest path graph between 6 and 11 in F. So far, we have introduced our proposed method query by sketch, and to evaluate this method, we compare it with several baselines. The bidirectional BFS is a search-based method, and both the parent path labeling and parent parent path labeling are labeling-based methods. We conduct our experiments on 12 real-world datasets. Among all datasets, the largest one, ClueWeb, has 1.7 billion vertices and 7.8 billion edges. We can see that for all these datasets, the maximum degree is orders of magnitude larger than the average degree. In fact, previous work shows that these large degree vertices are more likely to be on the shortest paths between other vertices than low degree vertices. So we choose vertices with largest degree as our landmarks in query by sketch. The first question we want to answer is that how efficiently can query by sketch construct labeling scheme? We tested the construction time under 20 landmarks. DNF and ROM refer to do not finish in one day and running out of memory, which is over 500 gigabytes. This table shows that compared with the labeling-based methods, our method query by sketch uses a significantly less amount of time for constructing the labeling scheme, and it scales over networks with billions of vertices and edges. Then, how does query by sketch perform in terms of labeling size? We compare the labeling sizes of these methods against the size of datasets. Unlike labeling-based methods whose labeling sizes are times larger than the dataset itself, the labeling sizes of query by sketch are mainly smaller than the datasets. The third question is about the query time efficiency. Here we randomly pick 10,000 vertex pairs as our queries, and we compare the average query time. As shown in this table, our method query by sketch is much more efficient than bidirectional BFS. Even for the largest network, it can answer a query in less than 0.5 seconds. The parent-parent path labeling is also efficient in answering the queries. It is not scalable since it's computationally expensive to construct labels. Now, the query time efficiency, labeling space efficiency, and the scalability of query by sketch were preliminarily verified. We further want to know why our method performs, how sketch improves the performance. So we test our method using different number of landmarks. Here, pair coverage ratio refers to the proportion of queries that the sketch captures the shortest path between query vertices. The light color denotes the ratio that all the shortest paths between query vertices are captured by the sketch. And the gray color denotes the ratio that the sketch captures part of shortest path information, while there remains some shortest path in the specified graph. For most datasets, the sketch we compute is quite useful in estimating the shortest paths between query pairs. We can see that both ratios go up when we have more landmarks, but the increasing rate generally slows down. Therefore, a question comes very naturally is that how the number of landmarks affect the performance. Will more landmarks always lead to a better performance? We first test the construction time and labeling size under different number of landmarks. Generally, the construction time improves linearly and the size of labeling increases when the number of landmarks become larger. This figure shows us the impact of varying landmarks on query time. When the number of landmarks increases, the query time may increase, decrease, or have no significant changes. This is because that the removing more landmarks can better specify the graph and leads to a more accurate sketch. The time for computing shortest path in the sketch also increases. In conclusion, we have proposed a novel method, query by sketch, to answer shortest path graph queries on large networks. Query by sketch constructs a labeling scheme through pre-computation and then answer queries by performing online computation that involves fast sketching and guided searching. We have conducted experiments on 12 large real-world datasets to verify the scalability and efficiency of query by sketch. We have also proved the correctness and analyzed the complexity of query by sketch. Please refer to our paper for more details.